introduction. Well, been working on X for probably 15 years. Started with working on a single driver and worked my way up through X, and was around when all the changes happened inside X, and my work recently expanded to a lot of components of the graphics stack that are no longer in X. I'm doing a lot of kernel work these days. And today, well, I'm going to talk about Wayland. You all probably have heard something about Wayland, otherwise you wouldn't be here today. So, what is Wayland? So, in short, it's Wayland is a display server framework. So, under Linux, we do have a display server. It's the X Windows system. Why do we need something else, or why do some people think that we need something else and the X Windows system is not providing what we need to go forward? And this is something that I want to kind of outline in this presentation. So let's take a look how X used to be until very few years ago, how the X server looked like. Pretty much you had the server as a single component that contained everything from the drivers to the protocol layer. It handled the input events directly. It had drivers for all kinds of input devices, talked to serial devices, and later on to PS2 and whatever devices. It had video drivers integrated. All those video drivers in the past used to live in user space. And you had clients that connected to the X server, sending requests for the X server to do something. Okay. Okay. And those requests involved commands to draw things like simple graphics primitives and fonts. And also the X server maintained a window hierarchy, so an application didn't just have one single window it drew in, but it had a rich layer of stacked windows for all X applications. Each button was a separate input window. So it maintained all these things. It managed grabs. So if you press the mouse button and on some button and moved away, so the input window would remain the same even if you left the window with your mouse and changed the focus. So the X server used to do all these things. Okay. And what you see here outlined with a blue background is actually what is the core X. So any implementation of the X Windows system, release 11, needs to provide these core functionalities. Even though a lot of those functionalities, as we will see going on, are not used today anymore, this is what makes X. And any X application talking to the X server needs to, or can expect that these things exist. Now the drivers, this was a specialty of the implementation we had on Linux and other free operating systems. Didn't necessarily have to be in the X server. It was just an implementational detail. Oops. So, how does rendering work under X? still does today. Usually, the X server draws something as a result of some user interaction. For instance, if the user presses a mouse button. So today, our input drivers are no longer in the X server, but they are in the kernel, and the X server is just talking to the EVDEF device, which provides a generic protocol. The X server needs to interpret and get the input events. So the user presses a button, the hardware sends the event, and the driver will interpret, the kernel EVDEF driver will interpret it, and then we'll send an EVDEF event to the X server, which in turn will look through its windows, its window stacking order, and according to the location of the input of the mouse cursor, it will determine to which client to send this event and to which window this event goes to. And then it will send an event to one of the X clients that are connected. This client receives this event, and actually input events mouse. It will then take some action, maybe paint a button. So it will send a draw request to the X server. Now, today modern applications hardly use any of the drawing primitives of X anymore. They usually send over images which are either drawn to Windows directly or drawn into pix maps. So the client will send a request to the server to change something on some window as a result of this event. And then today, most cases we run a composition manager or compositing window manager. So the X server will then perform the actual drawing, but it will not draw to the screen, to the scan-out buffer from where the image which you see gets generated directly, but it will just send the drawing request or the image data into an off-screen representation of the window. And then it will notify the composition manager with which it shares this window buffer, the buffer where this window data is stored, of a change in the window. It will send a damage event. And then the composition manager, who's actually in charge today of assembling everything that you see on the screen and put windows in the right location, will then go and determine where on the screen this change needs to get drawn. It will then update the screen, or will update the front buffer, the scan-out buffer, and then we'll tell the X server about it, and the X server can then go and display this buffer. Usually today it would just do a page flip to the new buffer. And this will get sent to our kernel driver, the KMS driver, which handles the graphics, and from there it will go to the hardware. So if you look at this picture, you'll see quite a few context switches. Everything goes through the X server, but if you follow things closely, you will see that the X server is just a man in the middle that is not really needed anymore, because everything here is actually drawn by the composition manager. The composition manager will just get the content of the window and then assemble the whole screen. So we have quite a few context switches here and quite a few round trips that we don't actually need. So another thing that you've probably that kind of got outlined already, a lot of components that we used to have in the X server in the past have moved out of the X server. For instance, our graphics drivers are no longer part of the X server. They've moved into the kernel. Our input drivers are no longer part of the X server. They're also in the kernel. Modern applications, modern toolkits use things like font config to draw fonts, so you don't need actually the font drawing capability of the X server anymore. To draw window contents, modern applications will not rely on the drawing primitives that the X server offers because they look kind of ugly. They're not anti-aliased. Lines are jagged, and those drawing primitives are kind of limited. So they will much more rely on libraries like Cairo or Qt that have their own rendering capabilities and will actually draw the entire window content. There's kind of wind noise in here. It's better now. Okay. So there's a lot of functionality in the X server that modern applications actually don't use anymore at all. Another thing is that modern toolkits abstract away a lot of the internals of the X server. So if you want to migrate to something else than the X Windows system, you don't have to change each and every application that uses these toolkits. You just do the changes inside the toolkit itself. If you look at toolkits like Qt or JTK, they already run on other systems like Windows and Mac OS. So on the infrastructure, to move away from a display server system is already in place. Also, modern toolkits don't use things like sub-windowing anymore. Today, for an application today, a window is just a single canvas, and the application will determine itself where the input events go to and which action you want to perform when you click a button. It's no longer the X server that determines the sub window where the click went to and will notify this sub window. This is all done inside the toolkit already. So so we see here that X is actually just a passive middleman that's in the way, and that's kind of just dispatching jobs around. Oops, that was too fast. So what can we do if we want to get rid of this middleman that seems to be no longer needed? So we shift the responsibilities to operate and talk and draw things away from the X server to the composition manager. And so that the input events get sent to the composition manager directly, and the composition manager can then itself talk to its clients. And then we have a lot fewer task switches in between. And the clients, as modern toolkits do this anyway, they can directly draw into their windows. It's no longer that they have to use the X protocol and send an image or a rendering request across the X protocol to the server, which then will actually update a window back buffer. It's the application could actually go and allocate its own window buffer and draw to it, and then pass this to the composition manager. Okay, and that's what's actually happening. So Wayland is an infrastructure that implements this change. So if you make the composition manager your main entity, the following thing will happen. So the input event will go to the kernel as before. Nothing has changed there. So we can reuse all this infrastructure, but from there the compositor will read it directly. The compositor will then go through its scene graph and determine itself where the input event goes to. And the good thing about this is the compositor is able to do transformations. It can, for instance, zoom windows or project them on. Okay. Okay. Okay, so nobody's running out. Okay, so the compositor itself can do transformations. It knows exactly where the windows are located. And so, for instance, if the compositor has transformed the window, for instance, rotated it, it then can determine where the input event goes to by actually doing the reverse transformation. In the X Windows system, the X server had no idea of any transformations that the compositor did to the locations of the windows. And so the compositors were always bound to have their window locations or be in sync with their window locations with the X server, because the X server itself determined where the input event finally should go to which window. And although the composition manager had its own ideas of transformation, so those transformations were very limited. Now, with the compositor in charge of both handling the input events and also the knowing of the exact location of the windows on the screen and their transformations, it can then determine much better where to send this event to. And it will identify the window it needs to send this event to and send this to the client owning this window. And the client will then go and take the action and do something in response. For instance, update something in its window, paint a button or write some text, and it will just render into a buffer that it has itself allocated as the and paint directly in there. And once it is through with the painting, in the X protocol, it was a constant stream of drawing operations. The X server had no idea when the client was actually done. It could actually just check if there were more requests in the queue and assume when there were no requests that the client was done. But there was actually no way for the X server to know if the client was actually done. The client could wait for the requests to be processed by doing calling xsync, but the server never knew when the client was done. Now the client can do all its drawing, all the screen update as the result of a user interaction or whatever, and it knows when it's done with the drawing, and once it has finished the drawing, it can then pass this buffer over to the compositor and tell the compositor, oh, by the way, in this buffer, this and this area has changed. And then the compositor, this is this step, and then the compositor can take this buffer and update and go through its scene graph and determine where on the screen this window needs to be located and how it is rendered. Take the data from this buffer and paint it on the screen. It can take different ways of doing this. Most often, since we are using OpenGLES on this, it will just take the Windows content and texture from there into the screen. And the client itself is free to do whatever, to use whatever it wants to draw to this screen. It can also use OpenGL or OpenGLES. It can use OpenVG or draw directly. This is all up to the client. The client just needs to pass this buffer to the Wayland server or to the Wayland compositor. Yeah. Once the Wayland compositor has updated its back buffer, it then will go and tell KMS, please switch, do a page flip or whatever, and display. And if you compare this picture with the previous one, you will see a lot fewer task switches in there. So your drawing can be done much more smoothly. Okay. So what is this buffer sharing? So in the idea of Wayland, the display server just allocates its own back and front buffer. The window buffers are in charge, are allocated by the clients itself, themselves. So the clients are responsible of allocating their render buffers, or usually in the Wayland implementation that we currently have, it will on Linux it will just get a gem buffer from the kernel and draw there, and then pass a buffer handle through to the compositor. How this is done, I will explain later on a slide discussing the Wayland protocol itself. So the client actually just renders into its buffer, as I explained, and will then just submit it to the compositor once it knows that it's done. And so that the compositor, however, will not update anything on the screen unless it also learned about the areas where things have changed. So this is something that was also taken from a lesson taken from X. We notify the compositor of areas that have changed, so we just have to do in many situations we just have to update a minimal area and not the entire screen. Of course, with this same mechanism, we can also implement video overlays, for instance. Videos usually have a different color format. They're not RGB or RGBA buffers, they're YUV buffers. But this is not a problem. There's something so that the Wayland compositor can then go and determine which format a buffer is in and adjust its rendering, for instance the text string, accordingly. You can use the texture engine to draw a YOV buffer just as well as an RGBA buffer. It just needs to be set up differently. Or, for instance, the entire hardware is to the disposal of the composition manager, so it can determine if it has some other rendering plane, maybe an overlay plane, which can itself do YOV decoding, and then just make the window or the window buffer with the YOV data the buffer for this plane. So the graphics engine will then render directly out from this window buffer into the screen, and the data will never hit the CPU in the compositor. And something else which is also very important, the client can ask the compositor when the window content actually became visible on the screen. So usually what happens in the compositor will go and update the back buffer, and when it's done, it will usually on a vertical retrace, it will do a page flip and display the new buffer. And then it will send an event with an exact timestamp when this happened back to the client. And from there, the client can do very exact timing, for instance, for video playback. It will know exactly when the buffer that it sent before was displayed, and can then throttle its rendering accordingly to have a smooth video rendering. Okay, so how do the clients in Wayland how do clients in Wayland talk to their display server, to the compositor? The protocol that is used is very much inspired by the X Window System protocol. It's a lot of ideas that already existed in the X Window System protocol exist here again. So it uses Unix sockets to talk to the composition manager, to the display server, and to pass information about the buffers to the composition manager. It will pass a file handle through the control channel of the Unix socket. The protocol, the protocol is designed so that functional systems are combined to what is called interfaces. And a display server will offer a certain number of interfaces to the clients. When the client connects to the display server, the first thing it does is query which interfaces are available. Interfaces are identified by unique names, and what the display server does, it sends back a list of interface names together with unique IDs which are valid for the lifetime of the whole session. And those IDs are 32-bit integers, like everything else in the protocol. This was actually a lesson that was learned from the X Window System, that it's no good to have 8 or 16-bit entities in your protocol stream, because then it's depending on the architecture you're running on, it's much more work and takes much more CPU overhead to decode the stream. So everything in Wayland are 32-bit integers, or things like strings are then padded to 32-bit. Like the X protocol, the Wayland protocol is asynchronous. Same request, reply, and event structure. The good thing about the Wayland thing is, if you recall what I explained, how the buffer handling works, there are very few instances where the client actually needs to wait for a reply from the server. So you have very few round trips and very few situations where you have to wait. For instance, when you start up the client and it asks the server for the available interfaces, of course it has to wait. But all this rendering is done just in a push operation. There is no need to wait for anything, except maybe for an event which gives you the timestamp back that I explained before. But this is something the client can ask or not ask for. Okay, there is one of the touchy issues. Now, if you followed what I just explained about the protocol, it has this one thing, the buffer sharing, which is done through a file handle that gets passed through a Unix through a controls channel on in the Unix socket. This the big thing is in Windows, in X, people say, well, we are wire transparent, and and it's one of the big features of X is the wire transparency. I had the impression for in the last years that only very few people are still using the wire transparency. Most applications run locally, and people are not really interested in it. And then when Wayland came out, I thought, well, maybe this is the consequence from it. So how many of you are actually running X clients remotely? There are quite a few hands, but not everybody. Okay, so but the density of people doing the more advanced things should be higher here than. But when Wayland came around, people noticed, of course, it was not wire transparent, and then they started crying, "Give me our wire transparency back! How can you ever design something and expect it to succeed if it's not wire transparent?" Well, what can we do about it? And of course, you cannot share a buffer across a wire. I mean, a buffer is located in memory, and the memory is local to your machine. But if you followed what I explained before, of course, the buffer content needs to be copied over over the wire somehow, and this you just cannot just handle over a file handle. But this is not really a big issue. If you look at what I explained before, the client already informs the server of damage. So it informs the server of the area on the screen where things have changed. So from this, you can really minimize the amount of data you would have to copy from a client machine to a server machine. So, and another thing that is really good, and that's much better in the Wayland design than in the X design, is that you have very few round trips. Round trips always hit people badly on high latency networks. Try and display a window over a DSL line and you will know what I'm talking about. This is not slow, not because of the limited bandwidth of the DSL line, but it's slow because of the many round trips that take place, and the DSL line has quite high latencies. So actually, Wayland is the Wayland design is actually very suitable to be made wire transparent. The only thing is what needs to be added, and there are some prototypes around already where this has taken place, is that the buffer content gets copied across the wire. This will involve some data transfer, which is not that much due to the fact that we know exactly which areas have changed. And you probably don't have to do anything in the client, just in the libraries below, to implement wire transparency for this design. And if you look at X clients today, they, as I explained before, they do already a huge amount of pixel transfer because they don't use the old style graphics primitives of the X server anymore anyway. So we don't expect that if we implement a wire transparency for Wayland that this will be any worse than what we have today with X. Okay, I just talked about Wayland, and as I said in the beginning, Wayland is just a display server framework, and with a framework you cannot do much yet. So, and I was talking about a composition manager or a compositor, a Wayland compositor. So, the idea was originally that the desktop projects that had composition managers or compositing window managers already decide to port those to Wayland so that we would have many implementations of display servers. And as I explained earlier, the system with the interfaces is very flexible, and each system could also add their own interfaces and add features whatever they like. So it was expected to take advantage of this flexibility of the infrastructure that is provided. So far, not much has happened, and the Wayland developers itself had developed a proof of concept composition manager to test the things that they've implemented in the framework. So this thing became quite capable already. It's not a full-blown desktop system like you have on KDE or GNOME today, but for simple tasks, like if you need to have a multi-context display where, for instance, on a set-top box or in a car display, where you need to switch between different applications, already quite usable. And a lot of people today, the more advanced developer type people, kind of switch away from heavy KDE and GNOME and go more to things like XFC, and it's expected that this reference implementation is actually able to, or a lot of the design from XFCE or similar things could easily be implemented in this reference design. This reference design compositing manager is called Weston. Probably you've heard about this a bit. One of the reasons that why the Kwin and Mutter and the other compositors for X have not jumped ship and joined the Wayland crowd yet is very likely that the interfaces in Wayland have been a running target in the past. This is one thing that will be fixed pretty soon. because it's planned to have the 1.0 release probably next week on the 24th. Don't bet on this. It has been pushed forward in the past, but it's scheduled to happen pretty soon. And from there on, there will be no incompatible changes anymore in the protocol. So we expect to see more activities inside other display servers. But we can already take a look at some of the things that Wayland can do by taking a look at the reference implementation in Weston. Oh, and there's another interesting topic. This is, X has been around for 25 years now. The 25th anniversary of the X Windows system, release 11, was about 4 weeks ago. Today, I think it was actually today, 3 or 4 weeks ago. Michael knows probably better. So it's been around for quite a while, and there are bazillions of clients and applications using the X Windows system. So we'll probably cannot expect it to go away that soon, and it's actually not planned that there will be a certain date where everybody will just switch on. So what can we do? What can we do to run X applications in a Wayland environment? And there is also a reference implementation for this in Weston. I will show this in a demo shortly. So yeah, let's see what's happening there. Now we have the Wayland Composition Manager, Weston or something else, several clients, Wayland clients connected to it, as explained before, and now we have an X client that wants to talk to an X server. Now what happened? What the reference implementation does, the Wayland compositor actually listens for on the well-known socket, Unix socket, where X listens for X clients to connect. When it sees an X client connecting, we'll just go and start an X server. And it's a specially built X server that is capable of sharing buffers with the Wayland compositor. And then it will transfer the X client to this X server, and this X client will then regularly connect to this X server, and as it was running on the server from the beginning. Then as soon as the X client opens up a window and maps this so it becomes visible, this X server will then act as a Wayland compositor client and allocate a buffer, a rendering buffer, for this window, and share this buffer with the Wayland compositor. So let's see what happens when a user pushes a button. So we will have the same thing as before. The EVDEF driver will be notified. The EVDEF driver will then notify the Wayland compositor. The Wayland compositor will then go and determine where the event goes to which window. It will determine it goes to an X window that it's currently rendering, so it will send it to the X server. So the X server will from there on go and send the event to the X client, and this will do some rendering, send it back to the X server like normal X clients do, and then the X server will update the shared buffer that it shares with the compositor, update the window content, and from there it goes back to the Wayland compositor, which assembles the scene on the screen according to its understanding of the layout. and it will notify KMS to draw things to the graphics card. Thank you. This, if you look at the task switches that are involved here, you will discover there it's the same as on the first slide, where you had the compositing manager sitting on the side of X. So it's actually pretty much the same situation, but we have gained one thing. Since the input events are sent to the Wayland compositor first, this can already do the transformation, the reverse transformation, and determine to which window the input goes. So we expect that X clients on Wayland will have exactly the same performance as they have today. In an environment where you run your X clients on X, which talks to a composition manager on the side. Okay, so we'll use the remaining time to do some demos. I'll show the... Sorry. I hope it works. I've never done this with a projector, so yeah, it's this. Yeah. Yeah, I will try what I can. I will see what I can do here. Oh, something actually happened. Okay. So here you see the Weston Wayland compositor. It's can open Windows here. It's a terminal that's actually a Wayland client written for this thing. Yeah, and there's one thing I can point out right away. Oh, there's. Oh, okay. Not sure how to get it. Ah, there we go. Yeah, this is another thing. Weston doesn't have clone mode yet, because clone mode was actually just a limitation because of certain stride limits on graphics cards, and it's not really useful except for presentations. So has not been implemented yet. But there's nothing that would actually prevent it from being implemented. It's actually very easy to do, because instead of texturing to just one buffer, you would texture the same scene to two buffers. It's really no issue. Okay, now I have to look up here because I don't see anything down here anymore. Yeah, this is kind of confusing now. Now you can do things like, oh, it's kind of awkward. Oh, this is actually not what I wanted. Try it again. Move it over. There you can rotate your window. For instance, this is something that wouldn't be possible in X, because in X, the X server has no idea of any rotation that the composition manager does. So here you can actually, what the heck? due to the release, there's a lot of activities in development, and if you just pick random Git snapshots, not everything may be working, might be okay there. So yeah, you can see it. Composition Manager nicely transforms the input events so it knows exactly where this goes. There's another thing that you will see here. You notice this line? It's rendered nicely. The border between the window and its decoration. This is a very highly debated thing, because Wayland currently has the concept of client-side decorations for Windows. In X, the decorations are all done by the window manager. Okay. Under Wayland, it's currently the plan to have the decorations on the client side, exactly for the reason that you can then go and render things like borders between the decoration and the window content much more smoothly, as if you had just the window and then nothing as the background. You cannot do all the inter-aliasing that you do when you do transformations. So what else can we do? For instance, oops. Yeah, that's not gonna work. Hey, this is. Sorry. No. Yeah, yeah. This was stupid. Display 1 was correct. Actually, I'm not sure why it's not starting. It used to work yesterday. I just set up this laptop with all this stuff and built all this stuff, and it used to work yesterday. So, what else can we show? Maybe. Sorry? Yeah, moving is this is no issue. Oh, there. You can also do. Let's see. What was the key sequence? This is the nice thing. You can mouse around here, move this out of the way. But when you start typing, it will jump back and bring the area to the center. Yeah, I'm sorry. I'm not sure why the X demo isn't working at the moment. Maybe you can catch me later, and then I can show you. For now, you have to trust me that it actually works. I think we're pretty tight in time, so maybe we should just go over and see if there are any questions. Olaf. I mean, you have your windows, and you can have OpenGL or Mesa draw into those windows, and then those windows get passed over to the Wayland compositor, and this will, at least this here, will use Mesa OpenGL ES again to update the screen content. So this is all actually very much relying on Mesa and OpenGL. the reason why the composition manager is not using OpenGL but OpenGL ES is that OpenGL in Mesa, it's an issue of the implementation. At the time when it was started, had too many X dependencies, so it would pull in all the X libraries again when you loaded libgl, and this was the case with OpenGL ES. That's why it's done in OpenGL ES. But there is no fundamental reason why this thing couldn't be done in OpenGL. Yeah, I mean, there's, for instance, there are all different opportunities that the hardware offers. If the hardware, like I explained, if the hardware offers you rendering planes for different color formats, or even RGB planes, the composition manager can then go and decide, oh, this is a full screen window. I don't need clipping there. I will just use the window buffer that I got passed from the application as a rendering plane, and just notify the hardware to use this rectangle and not render from the scanout buffer, but from some other buffer which contains this plane. You can actually avoid all the texturing. You don't have to go through the GPU, which is very important, especially on embedded devices like phones, where you're kind of battery limited. The GPU, when it does 3D rendering, is very power hungry, but those dedicated overlay planes take up a lot less power. So if you're in the embedded community doing those phones and stuff, you will see much more overlay planes used than 3D engines. I mean, this is and the compositor can actually, because it has all this hardware features as it to its disposal, and has the knowledge of the location of windows, it can decide if it wants to texture into the front buffer, into the scanout buffer or the back buffer, and then flip it to the front buffer, or if it just wants to use the data as a separate scanout buffer for an overlay plane. And if you have a hardware video decoder, you can just, if there is a common format, which is not the case on Intel, but if there is a common format between the hardware video decoder and the screen overlay plane, you can just go and take the data that the hardware decoder wrote into the memory and point your GPU at it and tell it this is the overlay plane. So it never hits the CPU. There is no copying around. There are all these possibilities. Yeah.
So you were talking about KDE and Genome jumping on the train of Wayland. Actually, they are waiting KDE for Qt5 to be released.
Yeah.
Because only there's the Wayland backend working right now. My question is, when no 3D accelerated GPU is found, will Wayland actually require LLVM pipe?
Yeah, I mean, I'm not sure how fast this will be, but it should work, because this is just sitting on top of OpenGL, and it's just pushing buffers around, and those buffers are allocated through OpenGL. And you can just, whatever backend is underneath OpenGL or OpenGL ES in this case, it can use. So I'm not sure how performant it will be if you use. No, why? I mean, you can. It depends on the design of the composition manager. You can have one seat per display if your graphics card is able to drive 8 heads, and it can have 8 front buffers and render different contexts to it. Oh yeah, sure. Well, this is a different story. I'm not sure. Display link doesn't have a acceleration infrastructure. If you do this, this is probably not. I'm not sure if this has ever been tried with display link. Yeah. But from the design here, it can be easily done in a composition manager. That's no issue. I mean, you can define separate keyboards and input devices for each seat. There is already infrastructure in Wayland for multi-seat. It's just maybe that the backend is not really capable of this. But then maybe you have to design the composition manager differently, not get as carried away as here in this case. Maybe you cannot zoom and flip and fade windows, but this is the same thing as if you do X in the composition manager. On the display link adapter, you probably don't want to run a composition manager, or only a very conservative one. Okay.